right, so let's take a look. We looked at substitution yesterday. Remember, that was a good strategy for us whenever we could easily isolate a variable, right? Whenever there was, once you get rid of those. Thanks, Sean. We can't, listen guys, I don't want you to have, let me just say this now. I'm not okay with like headphones in here or phones or anything in this area. You know, once you get out of the lab, I'm okay with it, that's fine. You know, when you're working, if you wanna listen to music, I don't have a problem with that, but in here, no go. So if they're easy to isolate, if they've got coefficients of 1 or -1, we use substitution. And we looked at an example yesterday where, you know, we took this situation where we had a y that we could easily isolate, right? So if we do that, if we isolate the y, we wanna, remember I told you we wanna put a box around that equation. We substitute into the other equation, and then what that does, now think kind of strategically here. What does that do? When we substitute for the other y, what it's doing is it's getting rid of all the y's from the equation. So now we've got, and it could be the other way around, by the way. We don't have to isolate y, we could isolate x, right? We know that. But when I make this substitution, I end up with only one kind of variable, and that's an important thing in math, right? In algebra, if we can get the equation down to a single kind of variable, we can always solve for it. And so then we just do the algebra. We distributed the two, we collected like terms, and we isolated the x, and we found out what x was, right? Once we know what x is, it's all kind of smooth sailing from there. We just plug that value of x into our boxed equation. Remember, we'd have a box around this one to find y, and we're done. We can just plug that back into both equations to check both cases then, right? To make sure that it's working in both cases. Okay, so that's that's substitution, and now we want to do linear combination. Okay, so linear combination is the case that works when it's not so easy, when we have a situation where we don't have a variable that's easy to isolate. Okay, so I'm going to skip through these instructions and we'll just kind of talk our way through this example. So what about this case right here? Okay. None of the variables are easy to isolate. So what do we do? Do you remember? Yes, Ruby?
You have to do the y's and...
Okay, so yeah, what we want to do now with linear combination, and did you, I can't remember, did you guys say you called it linear combination or elimination? Elimination. I like elimination better because that's really what you're doing is you're eliminating a variable. We want to multiply either one, if possible, one equation, both sides through by a number. Sometimes we might even need to do both so that we can set this up to have opposite values of either x or y. Does that make sense? So in this case, I think when you see an example, and we'll go through two examples, when you see an example, I think it really helps. So you can kind of get this process down. So any suggestions here? What could I multiply? Is there a way we could multiply just one equation by something to set the equations up to eliminate a variable?
Could you multiply the bottom by 3?
Okay, we can multiply the bottom by almost, not 3, by -3. Because we want to get, if we've got, oh, I'm sorry, no, you're right. Sorry, you're right. I didn't see that negative sign. The top is -6y. The bottom is +2y. If we multiply the bottom equation completely through by 3, we're going to end up with a +6y, which is good. Then the -6y and the +6y add to 0. They cancel, right? So here's how I like to show that. What I do is, if we're going to leave an equation alone, I just put an arrow. If we're going to multiply by something, I put an arrow with the value that we're multiplying by in a circle inside the arrow, okay? So the top one stays the same, 2x minus 6y equals 19. Bottom one, if we multiply through by 3, what do we get if I distribute the 3 all the way through? What are we going to get? Negative 9x, good, plus 6y, keep going, equals 30. Okay, and now, when we add vertically, that's important. The y's go away, right? That's our goal, to get rid of one of the variables. How many x's do we end up with? Negative 7x equals 49. And so what's the one step I need here to get the x by itself? divide both sides by -7. And so, what do we get? X equals -7. Positive 49 divided by -7. It's -7. We're halfway there. Now what? Yeah, we get to plug that back into either one of the original equations. If one of them is looks simpler, use that one. I don't think there's any huge difference. Why don't we go ahead and plug into the bottom one this time? It looks like a little bit smaller numbers. So if we take this x equals 7 and we plug in right there, plug in for x, do you see that what we're going to get then is just, what, -3 times -7, right? Because that x is becoming a -7, plus 2y equals 10. Well, that's an equation we can solve. I can point to a single variable, there it is, so I can solve for it. Now algebraically, if I'm just careful. If we simplify this, what's -3 times -7? 21, good. 21 plus 2y equals 10. So what are the two steps in order I'm going to go through to isolate the y? First, I subtract 21, right, which covers that up, and then divide by 2. Good. Okay, so if we do those two things, if I subtract 21, I get what? What's 10 minus 21? -11. Divide both sides by 2. And I got it. Y equals -11 halves. I could write that as 5.5 if I want to write it as -5.5 if I want to write it as a decimal, but that's fine. I can just leave it as a fraction too. That's a simplified fraction, right? Make sense? Got them both. I can plug those in to these two equations to check it too, right? Okay, let's just go, I'll go through the PowerPoint real quick. Just review those steps. Okay, add the two equations, we got that right. We multiplied by 3. X equals -7. They substituted into the top, that's fine. Got our -14. Add that to both sides and get 33. Divide both sides by -6. And it works out to be -11 halves if I reduce that fraction. Okay? Write as an ordered pair. And we can check by plugging it in. Okay, so what about something like this one? What strategy should we, what strategy is prescribed here? Which one would be? Okay, you could. There's going to be a couple questions on the assignment that are going to ask you which is the easiest solution to use. Here's how I want you to think about that. Can we use substitution conveniently there? Is there a variable we could isolate?
Yeah.
Yeah, which one?
Y.
The y in the bottom equation, we could. So when it asks you, so the correct answer as far as the assignment is concerned is, yeah, substitution. I don't know if I necessarily agree with that. Personally, I always kind of like to just use linear combination or elimination. To me, I just find it a little bit easier to do. I don't care which one you use in this case. You can take your pick. But because we can conveniently use substitution, that's sort of what the assignment's looking for in this one. Right, so they're going to say substitution, just because it's easy to do. I don't think that's a bad idea, maybe, to start off with at least, because substitution is a method that we can use again and again and again, even in situations that get more complicated than this. Substitution is always a good option if it's available. So we'd solve the second one for y, plug it in, and what do we get when we do that? So if I plug in 3x minus 5 up here for y, I get this equation. Would you agree if I distribute the -3, I'm going to get a -9x plus 15? Now look what happens here. I just want you to tell me, how do you interpret this? The 9x minus 9x cancels, and I get that result.
So it's true.
So that's a true statement. So how do we interpret that? Infinite solutions, right. What kind of lines would produce that situation? Same lines. Not parallel lines. Okay, true, they're parallel, but in addition to being parallel, they actually overlap, right? They have to be the same line. Okay, what's it mean? Same line. Okay, Okay, so they have infinitely many solutions. All right, so one more. What are we gonna use this time? We gotta use elimination, don't we? Questions so far? Okay, what am I gonna multiply by? Bottom equation by 2, everybody agree? If I multiply the bottom one by 2, leave the top one the same, we get 6x minus 4y equals 14. So what do I get on the bottom then? Plus 4y equals 14. Okay, what happens when I add those up? Yeah, that cancels and that cancels. So what's left on the left side? 0 equals 28. Okay, nonsense, right? How do we interpret that? No solutions, yeah. So what kind of lines are those if they are no solutions? Means they never cross, right? Zero equals 28, huh? Two lines are parallel. Okay, no solutions. Make sense? All right.